Hey differential equations. As I said, this is going to be the second video of numerical methods. Last video we talked about kind of the conceptual what's going on with each of the methods, and this time around we're going to actually do some calculations. When you have a lot of just repeated calculations, really the best way to do this is through Excel. So I'll be showing you how to do this through Excel. If you haven't played with Excel much, then I'll kind of give you just a really basic idea of what's going on and then show you how Excel would actually do this. Okay, as I said, you're going to be doing a lot of calculations over and over again, and Excel or any spreadsheet program is really good for that. So let's do Euler's method first. I like just kind of showing what's going on, just kind of remind myself. So my dy dx is going to be 3xy, and it's kind of important that here we put our step size, which is going to be 0.2. And so one thing I like doing is I like having my iterations here, and then this one has only x and y. And so we start out with our initial conditions, and we have our first iteration all the way to our fifth iteration. And so our initial conditions are x is 0 and y is 1. And so our x is always going to be going up our step size. So one thing for Excel is that if you want it to do a calculation, you always have to start with an equal sign, and you can kind of see what I'm doing up here to keep an eye on that. So we want to start with our previous x value, and then to that we're going to add our step size. But we always want to go back to our step size. So I'm going to hit an F4 here, and notice that when I hit an F4 here that we have now dollar signs in there, and that's what's going to keep it from moving. So I can go ahead and hit enter, and then what's really nice is you can do what's called a fill handle, is you grab this corner and select and grab down, and it will automatically fill in these formulas. And notice the things that didn't have the dollar signs, they changed as I moved down, but the thing that did have the dollar sign stayed the same. Okay, so now let's go for y. Y, if we look at this, so now we've got to use those formulas. So in order, remember, we have to do an equal sign to say we have to do a calculation. So to get my next y value, I want to hit my previous y value plus my step, but I don't want that to change, so F4, times this now is my derivative. So my derivative says my 3 times x times y. So 3 times my previous x value times my previous y value. And we can hit enter. Didn't change much, and that was because of the x equals 0. But if I take this and pull it down, we will get my approximations over that entire interval. And so my last this one right here tells me that for my approximation, when x equals 1, y equals approximately 2.8. So when x equals 1, y equals 2.975,377. Okay, approximately. So that's my first approximation. Let's now go to my improved Euler's. So I went ahead and I have my dy dx here. So my derivative's here, my step is here. Let's go ahead and put in my iterations. So start with your initial conditions. 1, 2, 3, 4, 5. So my initial conditions are my x equals 0. And now I have a column for z because we need that first prediction and then a corrector. but my initial condition for y is 1. So just like we did before, we're going to start with an equal sign. For my x's are always going to go up by my step. So previous plus the step, but you have to do that F4 to get the dollar signs in there. And I can copy those all the way down. Okay, now for my z, start with an equal sign, is my previous y value plus my step that I don't want to change, F4, times my derivative right here. And so my derivative, we say, is 3 times my previous x times my previous y. And we should be able to hit enter, and that should look familiar. But now let's figure out what the y value is. So my y value here says my previous y plus 1/2 my step times, so my average of the two slopes. So, okay, start with an equal sign. My previous y value plus my step that I don't want to change, F4, divided by 2, times, parenthesis, my first slope. So this gets me my first slope. So first slope is 3 times previous x times previous y plus my second slope. So plus, now my second slope, but instead of y, we're going to do z. So again, my slope is 3 times, now this time we're going to use this x value plus, not plus, times my z value, and then close out my parenthesis. Okay, so now I can grab both of these at once and pull them all the way down. And so this one says that when x is 1, y is 4.3. That's a pretty big difference. But notice how we said that Euler's gives an approximation but isn't quite a good approximation. So yeah, that's where we're going. So when x equals 1, my new approximation says that y equals about 4.3. Okay, let's go to Runge-Kutta 4. So Runge-Kutta 4, I went ahead and I have my derivative there, I have my step there, I did my iteration and my x the same way that I did everything else. Let's start here with my m. So my m starts with an equal sign. I've got my step function that I don't want to change times my derivative. So derivative is 3 times my previous x times my previous y. Okay. My second m, start with an equal sign. My h that I don't want to change times, now it gets a little funky because I've got my derivative with some funky stuff plugged in. So it's still my derivative, so it still starts out with 3 times, but now my x value is going to be a combination of stuff. It's going to be a combination of my previous h plus my step that I don't want to change, F4, divided by 2. And my y value times, now my y value is my previous y value plus my, what I found in M1 divided by 2. Close that out. And, okay. So now we get to do that again. Now M3 is my step that I don't want to change times my derivative with some funky stuff in it. So now my x value is my previous x value plus my, oh, I need parentheses around that, won't I? Yep, because I've got a bunch of stuff in my x value. So my previous x value plus my step that I don't want to change, divided by 2. So that's my x value times my y value, which is going to be my previous y value plus now m2 divided by 2. Okay, now on to m4. M4 is equal sign, step that I don't want to change, times slope with these funky things in for x and y. So okay, my x, so 3 times my x value now is my previous plus my step. Now my y value is my previous plus m3. Nope, and I forgot something. Let's see. Oh, I got a double multiply in there. Yep, let's see how that one works out. Nope. Okay. Oh, I see. Okay. I put in, when I meant to put in a equal sign, I actually put in another multiply. Okay, there you go. And then my y value is my previous plus 1/6 times, open parenthesis, m1 plus 2 times m2 plus 2 times m3 plus m4. Close that out. Okay, let's see. Now we can grab all of these and pull this down. Didn't work. Let's see why. Why didn't this work? What are we pulling from? Oh, looks like I forgot to make a don't move it, didn't I? Let's go back to this. Okay, so escape out of this. All the F3s need to have. Oh, there's an F3 without dollar signs in it. Let's see if that works. Hey, all right. And so notice now when x equals 1, then y equals 4.4. And so that isn't all that different from what we got with the improved Eulers. So Euler said it was 4.3, and Runge-Kutta says it's 4.4, almost 4.5. And so the improved Eulers really isn't bad, but the Runge-Kutta does give you a way more accurate, like really, really accurate prediction of what that function, what the points of that function will be. I hope that makes sense. If you guys have questions, let me know.